Welcome everyone to the Spoken Nerd, the podcast about database technology. I'm your host Connor McDonald, and hopefully you've been catching up on the podcast episodes to date, because in the last episode I made a bit of a joke. There was some jocularity about the concept of trying to do a podcast episode with no visuals, no graphics, no PowerPoint about block internals, what the internals of a database block in the Oracle database looks like. But I thought it's time to get out of the comfort zone. Let's give it a go. Let's see if we can walk you through the internals of a database block just with the power of voice. If you would like to follow along with a true data block dump, check the podcast notes associated with this episode, and I'll put a link in there pointing to a screenshot of a block dump, and you can bring that up on your own device to actually follow along with some of the terminologies and data we talk about in this session. But this is certainly not mandatory. I'll do my best to explain things as we go. Don't get me wrong, we're not going to dive too deep into things here. I'll use the phrase once around the block. In Australian parlance, that often means we're just taking a casual jog, a little bit of exercise, just once around the block to keep ourselves fit and healthy. And we'll do a once around the block in terms of block internals. A good look at the basics of a block without trying to dive too deep into what's going on inside, but hopefully enough to give you an idea of the way we store data inside the Oracle database. The term block, I think, is a good term because from early childhood we refer to the term as building blocks, the atomic units into which we build greater and bigger things. And inside the database, the block is the fundamental unit of data storage. As far as I know, just about every database vendor does it. They might have different names. In Oracle, we call it the block. I think in SQL Server and DB2, we refer it to as a page. But they all have this atomic unit that they do all operations in. Before we get too deep into things, I do need to stress, heading down into block internals is a bit of a slippery slope because as application developers or DBAs, you really don't need to know what's inside a database block. It really isn't the first port of call when you're looking at trying to tackle a performance problem or some sort of database issue. It's all too easy to fall for the siren's call of deep diving into internals, but the reality is we don't often need it. The reason I thought it might be useful today is because it's useful as backing up your knowledge of the higher level components of the Oracle database. When we come to see things like why are rows getting locked? Why are we having blocking issues, etc.? Or why is a table consuming more space than I thought? Then being able to go back to those block fundamentals is useful. But I stress, this is not about going incredibly deep into a block for no real valid reason. You can rest assured I will not be reading any hex or hexadecimal output on this podcast because I'm sure the listening numbers will simply rapidly drop at that point. So if you're an uber geek, you're probably going to be disappointed, but we're going to try keep things very practical here. And of course, if the listening numbers drop anyway, then that'll be a nice little message to me to not undertake block internals again on a podcast episode. So let's jump straight into it. A little bit of revision from earlier episodes, namely the database, as you'd expect, sits on files, either on the operating system or some sort of volume manager. Those files are made up of segments. Anything that consumes space, a table, an index, etc., can be collectively called a segment. Those segments are made up of extents, the units in which the database allocates space to you as you require to grow. And those extents are made up of blocks, the fundamental unit. Typically, these blocks are 8 kilobytes in size. The Oracle database supports anything between a 2 kilobyte block size up to a 32 kilobyte block size on some platforms, not all. And if you go trawling the interwebs, you'll see there's a lot of blog posts out there about why you should choose a particular block size. And typically this ranges from small being bad, large being good. 4K is better than 2K, 8K is better than 4K, 16K better than 8K, and so forth. There's a lot of bad information out there, and rest assured, you're probably running an 8K block size on your Oracle database, and most probably, except for very niche conditions, that is totally fine. For the rest of this episode, we'll assume you're running an 8K block size, but the logic here applies to all block sizes. They have a lot of common internals. If we're going to look at a block, the first thing we need to do is find one. And the easiest way to do that is to grab an existing table on your database and go have a look in the DBA_segments view. For a table, you'll see two columns. One's called the header file and the other is called the header block. This effectively is the starting point for your table. Every table in the database has what we call a single block called the segment header block. It's effectively a mapping of where the rest of the table can be found. Similarly, there's a view DBA_extents, and for every extent that a table or index consumes, there will be a row in this database view. Each row will have two critical columns in it. The file ID, where that particular extent will be stored out on the operating system, and inside that file ID there will be a column called the block ID. That is the starting position in the file for that segment. We don't need to know the exact byte offset in a file for a database extent because the blocks are commonly sized. As long as I know the starting block, then I know that timesing that number by the block size is the point in the file in which my data commences. Thus, if I was to create a brand new table and insert a single row, that's going to create me a segment, and that segment I can find by looking in DBA segments and looking for the segment header information, and I can look in DBA extents for the first extent for that table. And that extent will be found in a certain file nominated by the file ID column, and the starting block for that table will be found by the block ID column. If you're familiar with operating system tools, that would be all you need in order to dump out an 8K block. I could simply log onto the operating system, assuming I have access to the files and they were stored in a conventional file system. I could simply use the dd command. The dd command supports a block size parameter, and if in DBA extents it said the block starts at block number 10, I could simply skip the first 9 blocks and then ask the dd command to output the next block, the next 8K of information. I'd probably pipe that through something like octal dump, the OD command, and there you go. I would have a hexadecimal dump of an 8K chunk of a file which represents a data block. You could think of that as being the hacker's way of having a look inside a data block. But rest assured, unless that's the kind of thing that makes your Saturday night a lot of fun, I wouldn't want to be sitting around probing into an 8K dump of hex to try work out what all the bits and pieces mean. To avoid that somewhat arduous exercise, the database itself offers you a facility to dump out a data block to a trace file and not have to trawl through hex to try work out what's going on. There's an alter system command that lets you dump out a block. The syntax is an alter system command. So if I was looking at data file number 35 and trying to get the 9th block in that data file because that's the information that came out of DBA extents, I would simply run alter system dump data file 35 block 9. The cool thing with the alter system command that does that is it is what's called a symbolic dump. It doesn't just grab 8 kilobytes of hex and throw it out to a trace file. It does some internal formatting. It tries to give you a nice representation of how to interpret that block. I stress the definition of nice here is fairly loose. These facilities generally have always existed for people in Oracle support to assist when customers have things like block corruptions, etc. And therefore, in terms of a nice interpretation, it's a nice interpretation for the support engineers who obviously have existing knowledge of how blocks are structured. For the novice, it can be a little bit confronting, but in reality, it's a nice facility to have. It is important to stress though, it's what we call a symbolic dump. We've taken that hex and interpreted it through the database to provide a more English readable view of the block. I like to think of a symbolic block dump as a bit similar to PowerPoint versus source code. On PowerPoint, I'll present a nice, pretty view of how my system design works. In reality, my source code might be a lot more complicated, a lot more convoluted, and harder to digest. A symbolic version of a block dump is a much easier to digest view of the block, but it might not necessarily be a truthful reflection of what's inside the block itself. The block dump in the trace file might have a different layout. Just because something appears at the top of the block dump doesn't mean it's actually stored that way in the real block itself. And obviously we might put extra information to assist support engineers in that block dump. Because it's not a documented facility, it obviously can change from release to release, and it has done so. So be aware it's not some cast iron format that you'll always see in every release of the Oracle database. But still, it's a very super cool way to learn about blocks. You simply open up the trace file, have a look, and as I said, it is almost easy to read what's going on. In this podcast episode, in order to keep it less than, say, 25 days long, we're only going to cover one block today, and that is a block that contains data. You might be thinking, well, hold on, it's a database. Surely all blocks contain data. And that's sort of true, but let me explain what I mean by we're only going to cover a block with data in this episode. There are lots of different types of blocks inside an Oracle database. There's what we call a segment header block, the very first block in a table that describes where the rest of the table blocks are. There's what we call an extent map block, an undo block, bitmap blocks, lob segment blocks, lob index blocks, control file blocks, sort segment blocks, index leaf blocks, index branch blocks, compressed blocks, index compressed basic blocks, index compressed advanced blocks, hybrid columnar compression blocks, etc., etc., etc. There are dozens of different kinds of blocks, each one having its own internal structure. That's a big undertaking if we're going to cover that, and I don't think a podcast is perhaps the ideal medium for that. So we're going to cover just the single most common block you're likely to encounter in a database, that is a data block. You've got a table, it's got some data, let's have a look at what's inside one of those blocks. As I mentioned at the start, we don't have any potential to present visuals in a podcast. Therefore, one thing I will refer you to is the Database Concepts Guide in the standard Oracle documentation. Just as a quick segue, that in itself is a fantastic read. Yes, it's a bit dry, but if you're fairly new to Oracle, the single best way to get a complete coverage of how the database works and how to use it correctly and efficiently, the Concepts Guide is a fantastic place to start. If you really spend the time and read it cover to cover, you will literally know more than most, even long-term Oracle professionals out there, and you'll be well on the way to building fantastic applications. But inside the Concepts Guide in one of the sections is a picture of how a block looks. The best way I like to think of it is with some metaphors. Please don't flame me for the poor quality of them. A data block obviously contains rows, and perhaps the best way of thinking of a data block filling up with rows is, for example, the game of Jenga, where you would simply start with an empty slate and take each piece of Jenga wood, being a row, and simply start building upwards from the bottom. Data blocks build from the bottom upwards until they're full. If you're unfamiliar with Jenga, maybe Tetris is a better metaphor. The data would come flowing down from the top of the screen, aka your application's doing inserts, and once again you would fill from the bottom, slowly working your way up. I should stress that, unlike Tetris, once you fill up part of a block, the rows don't disappear. That would be perhaps MongoDB instead. No, sorry, I jest. If you're unfamiliar with Jenga or with Tetris, perhaps a simple metaphor for you would be that of a jar or Tupperware container. It has a fixed size, an 8K block, and it's empty to start, and as you fill it, as rows come in, you simply fill it from the bottom until it gets to near the top, at which point it's full. Perhaps the jar or Tupperware container is the best metaphor here because typically those things have a lid, and obviously the lid is an important part of the puzzle. It is exactly the same with a database block. Rows flow into the bottom to fill up the block, but at the top we have some important information as well. This is what's called the control information at the top of the block. You can think of it like the lid. Because relational databases are self-documenting, you can actually see the size of the lid on top of a block. If you query $type size, you can see there's an entry in there called KCBH. I'm guessing something like kernel cache block header, I don't know, but it does say the size of that is 20 bytes. So 20 bytes is reserved at the top of the block for control information. What is in that 20 bytes? The first thing we have, the type of block. As I said, there are many different types of blocks, and we're focusing just on a data block. It also contains the block size. An Oracle database typically has a single block size across the entire database, but this is not mandatory. I can create table spaces with a different block size than that of the default for the entire database. This is very useful when it comes to plugging in table spaces from other databases which have a different block size. Thus, each block needs to indicate what its block size is because we are not fixed just to the single block size per database. In a nice revelation of how the database evolves over time, that block header information also contains a flag as to what type of block header it is. That sounds very recursive. This is because before version 8 of the Oracle database, block headers were slightly different. We had to make some changes around the version 8 timeframe, and so now it is conceivable that you could have different types of header information inside a block. Although I will say, I would have some concerns here if you still have some pre-Oracle 8 blocks floating around in your database. It's definitely time to upgrade if that's the case. Also, when you're looking at your block dump for this information in the control area of a block, you'll see lots of little acronyms that have the term DBA in them. DBA, RDBA, etc. This is not a shout out to our great database administrator profession. DBA stands for Data Block Address. Throughout the symbolic dump of an Oracle data block, there are many references to where the block itself is stored, pointers to other blocks that are relevant, and we'll come to that shortly. And all these things have data block addresses. As mentioned before, the symbolic dump is easier to read than hex, but it's not necessarily the most verbose thing. So when you see things like data block addresses or any reference to some other file or block information, typically even inside the block dump, it'll just be a string of hex. Luckily, if you want to go chasing these list of data blocks addresses around to see what a block is linked to in the rest of the database, if you look in the DBMS utility PL/SQL supplied package, you'll see there's some utilities there. One's called data block address file and data block address block. And that lets you take that hex, convert it to decimal, and it'll return you the file number and block number that actually got merged to form that piece of hex that we call a DBA or data block address. So when you open up one of these symbolic blocks for the first time and see big gobloads of hex, don't panic. If they're prefixed with the term DBA, they're probably a data block address, and you can use DBMS utility to go digging around to find other blocks that you might want to dump out. The next thing you'll probably see in the symbolic data block dump is various pieces of information that have the term SCN next to them. SCN stands for System Change Number, and we'll do a full coverage of that in another podcast episode, but you can think of it as the arrow of time or the entropy of your database. We often in our own applications use an ascending sequence number for every transaction that we do. It's often a surrogate key on our transactional tables. You can think of the system change number as being that surrogate key for every single database transaction. So every time I do something that's going to do a commit, I'm going to give a system change number or SCN to that transaction. It's the arrow of time for the database. Interestingly, inside this symbolic block dump, you'll also see a subsequence change number, something that you would never see exposed outside the data block dump. That's because a single transaction might actually consist of various sequenced tasks. For example, if I was to insert a single row into an empty table, when you do a block dump of that, you'll probably see 5 subsequences to that system change number. Now, how do we get 5 changes for simply inserting a single row? You can actually dig down into that as well by dumping out redo blocks, which we won't get into today. But those 5 sequence tasks just to insert a single row, you can glean from the redo information as being, I formatted the block because the block was empty, the table was empty. I set some locking information. I wrote out some locking information. I moved the high watermark, and then I actually made the changes to the block. That is 5 little tasks that were required to insert a single row into an empty table. They're the kind of things you see in the subsequence or the subsystem change number. Also in the block dump, you'll see a thing called the block status. This can convey several things, but the 2 things you would most commonly see is that the status of the block is clean or it is dirty. You may be thinking a clean block is one that has no changes to it, and a dirty block is one that has, for example, uncommitted transactions inside it. However, a better interpretation might be, does the block in memory represent its state on disk? If it is, you can think of that block as being clean. If not, you can think of the block as being dirty. Because one of the cool things the Oracle database does is even if you commit transactions and you've changed lots of blocks in memory, it doesn't have to waste a lot of resources to forcibly write those blocks down to disk immediately. It can leave those dirty blocks in memory, knowing full well that all those changes are protected by the redo logs, and therefore we can save resource overheads by not writing those blocks to disk all the time. Also in your symbolic block dump, you'll see various values that have the word checksum associated with them. DBAs listening to this episode will be familiar with the DB block checksum parameter, which defaults to true for most databases, which means that we have some checksumming information in our blocks to make sure that the data inside them is valid, because generally there's no good way back from a corrupt block unless you've got a uncorrupt version of it somewhere on backups or your standby database, etc. Whilst we're on the topic of checksums, one of the interesting things you'll see in your symbolic block dump is some of this header information I've been talking about is also written at the very end of the block, at the tail of the block as well. Now that seems to be a bit strange. Why would you duplicate some control information at both the start and end of the block? The explanation to this is because we are at the whim of the OS. The database runs on top of an operating system, and the operating system, you could say, is the final arbiter of how information is written down to the disk. As I said, most Oracle databases run with an 8K block size. So when it comes to writing out an 8K block down to disk by, say, the database writer in the Oracle database, the database writer will throw a command out to the OS saying, yes, please write this 8K block down to disk in 1 unit of work, please, because this is my atomic unit. The operating system will reply, yeah, that's not really my cup of tea. My file system is built on a 1K block size. Therefore, I'm going to take your 8K block and do 8 1 kilobyte writes, all probably in parallel, to the file system. The Oracle database kernel and ourselves will be blissfully unaware of this. However, when it comes to reading from the operating system, once again, the Oracle database will say, please give me an 8K block. The operating system will respond and say, yep, I'll go read a batch of 1K blocks from my 1K file system and consolidate them to give you the 8K you requested. But think about the issues that this might introduce. What if I'm writing an 8K block in 8 times 1 kilobyte chunks? I've written the first 3. The operating system has written the first 3 of those 1K chunks to disk. At the same time, someone else wants to read that block from disk. For example, your database backup software. When it reads its 8 kilobytes and the operating system is halfway through writing a batch of 1 kilobyte writes, there's a very good chance you might pick up some of that 8K before it was written and some of the 8K after it was written. You would have a logically corrupt block. Having some of that control information at both the very start of the block and the very end of the block is an excellent way of catching those things. You can compare the header and tail information to make sure that the full 8K database block has some integrity no matter how the operating system chose to chunk up that block when it was written or read back from the file system. That covers off most of the control information you'll find at the top of the block. Let's now jump down to the bottom of the block where our data will be. In your symbolic block dump, you'll see plenty of little acronyms describing the data you have in your table. Once again, there's a lot of control information sitting around your true data to help ensure the block's validity. Some of the acronyms you can expect to find will be T-size. That is the total amount of space that can be used, the total size of space that can be used in this block. It's typically going to be just a little bit over 8K. In the block dump, it will probably be in hex. Yes, it's a good time to get your scientific hex calculator out. You'll have H size, that's the size of the block header. You'll have N tab, that is the number of tables in this block. Hold on, you might be thinking, what do you mean number of tables in this block? Don't forget, a little used but very old and mature technology is the concept of table clusters inside the Oracle database, where multiple tables can share the same rows. For example, you might put the department table and the employee table into a common cluster and they can share the department number column. It can be very useful for co-locating your data. Clusters have pretty much fallen out of use nowadays, but the entire Oracle Data Dictionary is very strongly based in clusters. Hence, NTab is still relevant because we need to know how many tables may be occupying this single block. nrow is the number of rows in this block. And then we start getting into how to manage the space in this block. You'll have FRRE, the free row pointer. That is, where is the next place I should put a free row? You'll have FSBO. Where does free space begin? The free space beginning offset. And FSEO, the free space ending offset. What we're doing is mapping out where free space in the block is such that we can very efficiently add data to it as rows come in. One of the key things in the Oracle database is ensuring that insert speed is very, very good at all times. You'll have AVSP, the available free space in this block. That won't be the same as the total free space in the block because as you delete existing rows from a table, that might not free up sufficient space to be reused by other rows. Therefore, you might have little tiny fragments of free space in your block that don't contribute to the available free space. Now that the block itself knows where the space is, where we can add rows, etc., we can now have some control information to where your data rows are inside this block. You'll see the acronym PTI offset. This is effectively the directory of where your rows can be found inside this block. Because we fill from the bottom, the numbers generally you'll see will be in descending order. It might say something like row number 1 starts at byte 8000, which will be in hex in the block dump. Row number 2 starts at byte 7010. Row number 3 starts at byte 6912, etc., etc. The rows grow from the bottom, the high offsets in the block, and slowly make their way back to the start of the block, just like filling up that jar. And one final pointer there'll be in the control information will be PRI offset. Where is the primary or first row in this block? When it comes to doing, for example, a scan of this block, rather than having to read through all the various bits of information, in terms of efficiency, it is good to know how can I jump to the very first row in this block and commence my scanning from there. Finally, after all of that free space information, pointer information, row directory information, we get to your real data. And inside the block dump, your first row, like all good languages, is row number 0. Even rows themselves have control information to indicate the row data itself. For example, there'll be a thing called FB, which is the flags for this row. Those flags might be H, which means this is a header part of a row. A single row could be much, much larger than a single data block. I could have 25 columns, each with varchar to 4000. A single row might start in one block and span multiple blocks. So an H means this is the header or first part of a row. The flag might be D, which means this row has been deleted. The flag might be F for the first piece or L for the last piece of a row. If it has a P, it stands that this first column is actually not the first column of the row. It could be a continuation from a previous row stored somewhere else in the block. And if you see a flag of N, it means the last column in this row is not the final column in the table. It actually is going to overflow into other rows as well. All of these flags are designed to let you store rows that are larger than a single block. After the flags for each row comes the columns and the column data. In an earlier episode, I mentioned the fact that you can think of columns being stored just as a simple concatenation with a delimiter. That delimiter is just the length of each piece of data. So the first column, just like rows, is called column number 0, and you will have the length of the data followed by the data itself. Column number 1, the second column, will simply then follow immediately after that with its length and then its data. Column number 2, which is the third column, its length and its data, and so forth. This is why, if the last, say, 10 columns in a row are all null, we don't need to store any information about that inside the row inside a data block. The last not null column will have its length and then its data, and that will be the end of it. We don't need anything else because everything else will be null. Conversely, if you have nulls within the middle columns and then later columns do have data, we do have to store something for those nulls to make sure the database knows that each one of those null values is in a particular column because data will come later. And all we have to do is store the length information for those nulls, the length being 0. Let's take stock of where we're at. We've covered the lid of the jar, all the control information that describes the kind of block, the SCN number, etc. We've covered the base or the bottom of the jar as it fills up with our row data and the various control information that relates to the rows. There is one thing left to cover, and that is in the middle of our jar. That is the transaction information. Who is doing stuff right now or recently to this block? In your symbolic block dump, you'll see a section there with the term ITL. ITL stands for Interested Transaction List. That is the list of transactions that are currently or have been recently active on this block due to DML from your applications coming in. The other acronym you'll see in this section is XID, which stands for Transaction ID. It will be a string of hex, but you can map this to the $V transaction table. If you look at $V transaction, there'll be 3 columns that are prefixed with the word XID. There's XID USN, which is the undo segment number, XID slot, which is a slot number inside the undo segment, and XID SQN stands for sequence number. Every open transaction that has an entry in $V transaction will have a registration somewhere in data blocks saying that this is an active transaction on this data block. Remember I mentioned the term DBA for data block address? You'll also see in the transaction area of a block a thing called the UBA, undo block address. To allow a transaction, we need to be able to undo it. Thus, every time we want to make some changes to a block, we have a pointer that points to the undo segment, the undo block address, to start the list of changes in order to back this transaction out, should we need to. I like to think of your ability to start a transaction is your ability not to make changes to blocks, but your ability to allocate some space in the undo segment. Once you're allowed to do that, then you're allowed to have a transaction. So just what exactly are these ITLs, interested transactions, etc.? Let's walk through a scenario where multiple people, multiple database sessions are making changes to this one block. Remember, we do row-level locking in the Oracle database. Multiple transactions on a single block doesn't mean we have blocking issues, no pun intended. Session 12 might be updating the 10th row on the block. Session 17 might be updating the 20th row on the block, and so forth. We can have multiple sessions all actively doing transactions on the same block with no concurrency issues. Let's bring ITLs into the equation. When session number 12 updates the 10th row on the block, if they are the first transaction, then they will be interested transaction number 1. There will be information for that transaction in the first ITL entry in this block. Session number 17, for example, is updating a different row on the block. They will be allocated the second transaction, therefore the second ITL slot on this block. The big question is, how many different sessions could all have concurrent transactions all on this same block? You may be familiar with the initrans and maxtrans parameters. That gives you up to 255. Maxtrans has always been set to 255. This means you can have 255 active transactions at any given point in time on a single block. But back to our sessions who currently have transactions on our block. If I have 3 sessions, each one updating different rows on the same block, how do I know which session is updating which rows? Yes, each session has an ITL entry saying, I'm currently interested in rows in this block, but how do I map the particular rows being updated to the sessions themselves? That ties back to the reason there is a cap of 255 active transactions on a single block. Every single row in the data block has one additional byte I haven't yet mentioned. This is called the lock byte. If the lock byte is 0, it means nothing is touching that row. If the lock byte is non-zero, and a single byte can have a value between 1 and 255, this lock byte is a pointer to the interested transaction list. Therefore, if session 12 is updating row number 10 with the first ITL, the lock byte in row 10 will be lock byte equals 1. If session number 17 is updating the 20th row with ITL number 2, the lock byte for that row will be 2, the value of 2. This is one of the cool implementations in the Oracle database. The cost, the resource cost of taking a lock in the Oracle database is effectively 0. Let me justify that. If I am updating an existing row, I'm visiting that row anyway to make changes to the data itself. while I am there, I am updating one additional byte, the lock byte, to indicate which interested transaction list has control over this update. I'm not making any other memory operations. I'm not updating any kind of lock database. I'm not preserving any kind of other structures. The cost of locking a row is 0. For the same reason, the number of rows you can lock in an Oracle database is infinite. There is no overhead. I often get the question on asktom.oracle.com, how do I get a list of all the rows that are currently locked in the Oracle database? You can't, because there is no structure that represents the list of all the locked rows in an Oracle database, because that locking information sits right there on the row itself. It's incredibly efficient. Let's wrap up our symbolic block dump episode today. Using our Tupperware container metaphor for a block, we covered the bottom of the jar. That's where all your rows go. But we also talked about the fact that each row in itself has some control information to nominate the kind of row information that's stored in there. We talked about the lid of the jar, the control information for the entire block, indicating the type of block, its data block address, and various other pieces of control information to ensure the block is valid. And sitting in the middle of the jar was our transactional information, the system change number and the interested transaction list, which is a reflection of what sessions are currently or have recently performed transactions on this block. Hopefully you've made it through to the end. I know we've had a fairly deep dive today into something which is fairly dry and perhaps not ideally suited to a podcast, but hopefully you've enjoyed listening. And if you would like to have a similar session, but perhaps performed over Zoom with some PowerPoint slides and some real-life demos on block internals, please hit me up on Twitter and we'll see what we can organize. Thanks very much for listening. We'll see you on another podcast episode soon while we keep talking about Oracle basics and making you more successful with the Oracle database. Bye for now. Thanks for listening to this podcast. The music credit goes to Zanman from Pixabay Music.